Welcome. Today we're diving into one of the most fascinating concepts in object-oriented programming, polymorphism. This principle allows objects to take on many forms, making your code more flexible and easier to maintain. Whether you're new to OOP or looking to deepen your understanding, this video will guide you through the essentials of polymorphism, its types, and real-world applications. Let's start by exploring what polymorphism really means and why it's such a powerful tool for developers. Polymorphism literally means many forms. In the context of programming, it refers to the ability of different objects to respond to the same function or method call in their own unique way. This means you can write code that works with objects of different classes, as long as they share a common interface or base class. This flexibility is a cornerstone of object-oriented design, enabling you to build systems that are both robust and adaptable. Why is polymorphism so important in OOP? The main advantage is that it allows you to write code that is more general and reusable. Instead of writing separate functions for each type of object, you can use polymorphism to handle different objects through a single interface. This not only reduces code duplication but also makes it easier to extend your program in the future. As your application grows, you can add new classes without changing existing code. Polymorphism in OOP comes in two main types: compile-time, also known as static polymorphism, and runtime dynamic polymorphism. Each type has its own use cases and implementation techniques. Understanding the difference between them is key to mastering polymorphism and applying it effectively in your projects. Let's break down each type and see how they work in practice. Compile-time polymorphism, or static polymorphism, is achieved through method overloading or operator overloading. This means that the method to be executed is determined at compile time, based on the method signature or the operator used. For example, you might have multiple methods with the same name but different parameters. The compiler decides which one to call based on the arguments you provide. Runtime polymorphism, or dynamic polymorphism, is typically implemented using method overriding. Here, the method that gets executed is determined at runtime depending on the actual object type. This is often achieved through inheritance and interfaces. For example, a base class might define a method and derived classes provide their own implementations. When you call the method on a base class reference, the correct version is chosen at runtime. Let's take a closer look at method overloading, a form of compile-time polymorphism. Method overloading allows you to define multiple methods with the same name but different parameter lists. This is useful when you want to perform similar operations with different types or numbers of inputs. The compiler selects the appropriate method based on the arguments you pass, making your code more intuitive and organized. Operator overloading is another example of compile-time polymorphism. It allows you to redefine the way operators work for user-defined types. For instance, you can define how the plus operator works for a custom class like a complex number or a vector. This makes your classes behave more like built-in types, improving code readability and usability. Now let's discuss method overriding, the core of runtime polymorphism. Method overriding occurs when a subclass provides a specific implementation of a method already defined in its superclass. This allows you to call the same method on different objects and get behavior that's appropriate for each object's class. It's a powerful way to ensure your code can adapt to new requirements without major changes. Inheritance is closely tied to polymorphism. By creating a hierarchy of classes, you can define general behavior in a base class and specialize it in derived classes. This structure enables polymorphism, as you can treat objects of different subclasses as instances of the base class and rely on overridden methods to provide the correct behavior at runtime. Interfaces are another way to achieve polymorphism. By defining a set of methods that must be implemented, interfaces allow different classes to be used interchangeably, as long as they adhere to the same contract. This is especially useful in large systems where you want to ensure consistency while allowing for flexibility and future expansion. See polymorphism in action with a simple example. Imagine you have a base class called animal with a method called makeSound. Different subclasses like dog and cat override this method to provide their own sounds. When you call makeSound on an animal reference, the correct sound is produced based on the actual object type. This is the essence of runtime polymorphism. Consider a payment system where you have a base class payment method and subclasses like credit card, PayPal, and bank transfer. Each subclass implements a process payment method differently. By using polymorphism, you can process payments without worrying about the specific type of payment method, making your code cleaner and more adaptable to new payment options. Polymorphism brings several benefits to your codebase. It promotes code reuse, reduces complexity, and makes your programs easier to extend and maintain. By allowing objects to be treated uniformly, you can write more general and flexible code. This is especially valuable in large projects where changes are frequent and requirements evolve over time. While polymorphism is powerful, it's not without drawbacks. One challenge is that it can make code harder to follow, especially for beginners. Debugging can also be more complex, since the actual method called depends on the object's runtime type. It's important to use polymorphism judiciously and document your code well to avoid confusion. It's important to distinguish between polymorphism and inheritance. While inheritance allows you to create a hierarchy of classes, polymorphism enables you to use objects of different classes through a common interface. Inheritance is about sharing structure and behavior, while polymorphism is about using those behaviors interchangeably. Abstract classes play a key role in enabling polymorphism. By defining abstract methods that must be implemented by subclasses, you can ensure that all derived classes provide specific behavior. This allows you to write code that works with the abstract class, relying on polymorphism to execute the correct method for each subclass. Java is a great example of a language that supports polymorphism. Through interfaces, abstract classes, and method overriding, Java enables you to write flexible and reusable code. The instanceof operator and dynamic method dispatch are key features that make polymorphism practical in Java applications. Python handles polymorphism in a more dynamic way. Thanks to duck typing, Python doesn't require explicit interfaces or base classes. If an object implements the required methods, it can be used wherever those methods are expected. This makes Python code highly flexible, though it also places more responsibility on the developer to ensure correctness. C++ supports both compile-time and runtime polymorphism. Method overloading and operator overloading provide static polymorphism, while virtual functions enable dynamic polymorphism. By using pointers or references to base classes, you can achieve flexible and efficient code structures in C++. C# also provides strong support for polymorphism through interfaces, abstract classes, and method overriding. The virtual and override keywords are central to implementing runtime polymorphism. This allows developers to build scalable and maintainable applications using the .NET framework. Polymorphism isn't just a programming concept, it's inspired by real life. Think about how remote control can operate different devices: TV, air conditioner, or stereo. The remote sends the same signal, but each device responds in its own way. This mirrors how polymorphism works in code, allowing different objects to respond to the same message uniquely. Many design patterns in software engineering rely on polymorphism. Patterns like strategy, state, and command use polymorphism to allow objects to change behavior at runtime. By leveraging polymorphism, these patterns enable flexible and maintainable code structures, making it easier to adapt to new requirements. Strategy pattern is a classic example of polymorphism in action. It allows you to define a family of algorithms, encapsulate each one, and make them interchangeable. By using a common interface, you can switch strategies at runtime without altering the client code. This pattern is widely used in scenarios where behavior needs to change dynamically. State pattern uses polymorphism to allow an object to change its behavior when its internal state changes. Each state is represented by a class that implements a common interface. The context object delegates behavior to the current state, making it easy to add new states or modify existing ones without changing the context code. Command pattern encapsulates a request as an object, allowing you to parameterize clients with different requests. By using polymorphism, you can create a variety of command objects that implement a common interface. This makes it easy to add new commands or change behavior without modifying existing code. Polymorphism is especially useful when working with collections of objects. For example, you can store objects of different subclasses in a single list or array as long as they share a common base class or interface. This allows you to process collections in a uniform way regardless of the specific object types. One of the greatest strengths of polymorphism is how it enables you to extend systems easily. When you need to add new functionality, you can simply create new subclasses or implementations of an interface. The existing code continues to work, and the new behavior is seamlessly integrated thanks to polymorphism. Polymorphism also makes testing easier. By using interfaces or base classes, you can substitute real objects with mock or stub implementations during testing. This allows you to isolate components and test them independently, improving the reliability and maintainability of your code. Maintaining large codebases can be challenging, but polymorphism helps by promoting loose coupling and high cohesion. By relying on interfaces and abstract classes, you can change or extend behavior without affecting other parts of the system. This leads to cleaner, more maintainable code that's easier to understand and modify. While polymorphism offers many benefits, it can have a slight impact on performance, especially with dynamic dispatch. However, modern compilers and runtime environments are optimized to handle polymorphic calls efficiently. In most cases, the flexibility and maintainability gained far outweigh any minor performance costs. Polymorphism works hand in hand with encapsulation. By hiding the details of object implementations behind interfaces or base classes, you can change how objects work internally without affecting the code that uses them. This separation of concerns is a key principle of object-oriented design. Abstraction is another core principle that complements polymorphism. By focusing on what an object does rather than how it does it, you can design systems that are easier to use and extend. Polymorphism allows you to interact with objects through abstract interfaces, making your code more modular and adaptable. Graphical user interface GUI frameworks make extensive use of polymorphism. For example, different types of buttons, sliders, and text fields can all be treated as generic widget objects. This allows the framework to handle a wide variety of components in a consistent way, simplifying development and maintenance. Game development is another area where polymorphism shines. Different game entities like players, enemies, and power-ups can all inherit from a common base class. This allows the game engine to manage and update all entities using the same interface, making the codebase more organized and scalable. Web development frameworks also leverage polymorphism. Controllers, views, and models can be defined using base classes or interfaces, allowing developers to extend and customize functionality without rewriting core logic. This leads to more modular and maintainable web applications. APIs often use polymorphism to provide flexible interfaces. By accepting parameters of a base type or interface, APIs can work with a wide range of objects. This makes it easier to extend APIs and integrate with new components without breaking existing functionality. Refactoring is the process of improving code structure without changing its behavior. Polymorphism makes refactoring easier by allowing you to replace specific implementations with more general ones. This helps you clean up code, reduce duplication, and prepare for future enhancements. Dependency injection frameworks rely on polymorphism to provide flexible and testable code. By injecting dependencies through interfaces or base classes, you can swap out implementations easily. This makes your code more modular and easier to test, especially in large and complex systems. Polymorphism is a key enabler of the solid principles, especially the open-closed principle and the Liskov substitution principle. By designing systems that rely on abstractions, you can extend functionality without modifying existing code and substitute objects without breaking behavior. Despite its advantages, polymorphism can lead to pitfalls if not used carefully. Overusing inheritance or creating overly complex class hierarchies can make code harder to understand and maintain. It's important to balance flexibility with simplicity and to favor composition over inheritance when possible. To get the most out of polymorphism, follow best practices like using clear and consistent interfaces, keeping class hierarchies shallow, and documenting your code. Always design for change, and use polymorphism to enable flexibility without sacrificing clarity or maintainability. Let's recap what we've learned. Polymorphism is a core concept in object-oriented programming that allows objects to take on many forms. It enables code reuse, flexibility, and easier maintenance. By understanding and applying polymorphism, you can build systems that are robust, adaptable, and ready for future growth. If you're interested in learning more about polymorphism and object-oriented programming, there are plenty of resources available. Books, online courses, and documentation for your favorite programming language can help you deepen your understanding and master these concepts. Keep exploring and practicing to become a better developer. Polymorphism is more than just a technical concept. It's a mindset that encourages flexibility, creativity, and growth. By embracing polymorphism, you can write code that's not only functional but also elegant and future-proof. Thanks for joining us on this journey through polymorphism in OOP. Keep coding, keep learning, and keep innovating.